We take a general video as input and decompose the input video into multiple components, which can be easily edited by human. After editing, we need to ensure that the edited component can be accurately integrated back into the video while maintaining the structure of the original video. Previous efforts have been evolving over time. Layer neural atlases have excelled in achieving precise video decomposition and component mapping. Deformable sprites have achieved significantly faster training speed. Both will suffer from inaccurate reconstruction of varying lighting effects and slow inference speed. Our work is the first work to consider spatial temporally varying lighting effects for layer-based video editing. We also achieve fast training, fast rendering, while being able to decompose high-resolution videos. We also show various video editing demonstrations. Let's start with layer-based video decomposition. We decompose each video into multiple layers, with each layer typically representing an object. The types of layers can be categorized into two groups, background and foreground. Foreground layer represents different moving objects, while a background layer represents the static objects and the static scene that remain unchanged. Each layer consists of several components, including a mapping function that translates the spatial temporal coordinates (yt) into textual coordinate (uv), predict mask for each time frame, an extracted texture of the object, and multiplicative residuals that capture variation in lighting conditions over time. Here is an overview of our method pipeline. We first take the spatial temporal location xyt as our model input. To sample color of each layer, we translate the xyt coordinates into UV coordinates. We outline the texture coordinates UV and apply an MLP to sample the base color. Additionally, we employ another MLP that incorporates the time t to sample the lighting condition. The masks for each layer are predicted individually, with video coordinates as their input. We employ hash encoding before the texture network and residual estimator to speed up convergence. Meanwhile, the mapping network is represented by an MLP without any encoding, as the output is intended to maintain smoothness. The residual estimator also considers t as an input, as the light conditions change over time. Due to the additive residuals dependency on the orbital term in diffuse shading, we adopt multiplicative residual. Further details can be found in our paper. The texture and light conditions of an object can be extracted through grid sampling. The sample texture can then be employed for video editing purposes. We largely improve the inference speed by catching all the components in memory, allowing the model to be executed in a single pass. For video editing, we extract the texture using grid sampling, apply modification to it, and then replace the original texture network with a modified texture to generate the modified video. For the lost details, please refer to our paper. Our method excels in video reconstruction across all three metrics, achieving faster rendering speed while keeping GPU memory and training time requirements low. We demonstrate various types of video editing. More results can be found in our project page and paper. Thank you.